Okay, so this is the third and final set of examples for this assignment. We're going to just look at creating a couple more Taylor-Maclaurin polynomials for some different kinds of functions. So this time, let's do a Maclaurin polynomial for cosine of x. When they say Maclaurin, that means implicitly you know the center of the polynomial approximation is designed to be centered around 0. So here's what cosine of x looks like, and we're supposed to find Maclaurin polynomials for this. So it looks like they want even ordered ones. I think sometimes you can only do even or odd. It depends on C. In other words, it depends on where you're wanting to do it, and it also depends on the function. So, I mean, you just have to see what you can do. So let's look at this one. So uh, once we do that, remember the first part of the process is to maybe just start taking some derivatives. So you take some derivatives, cosines, derivatives, negative sign, derivatives, negative cosine, derivative is sine. We wanted c equals 0, so we evaluate the function and its derivatives at that spot to obtain the coefficients. Remember we used those last time. And then we just start putting them in there. So p sub 0 is going to be just the value of f sub 0, right? That's what we would have had before. Of course, that's not going to be very good as soon as you get off that one point at 0. But anyway, the second order approximation, or the second order Maclaurin polynomial, you can say, is that value. We're just going to skip over the first order term, and we're going to go straight to the second order term, which is going to be minus 1. So you got your minus 1 from up there in the green box. And of course, second order always has a 2 factorial underneath times x squared, right? C is just 0, so it's not x minus 0 squared. X minus 0 squared is x squared. And then for the fourth order one, we grab this fourth order term. You can see that came from the fourth. This is going to be cyclical, right? So like the fourth order, even though it's not written down here, is just going to be 1 again. The fifth is going to be 0, then negative 1, then 0. It's just going to keep alternating in that 4-step cycle. So the fourth term would have a 1 on it, right? This is like the fourth. So that's why this has a 1 over 4 factorial. And then the sixth term, we're going to go down. So if that's fourth, then the sixth would be this guy. So it would be negative 1 over 6 factorial. There it is. Anyway, so then you can actually approximate specific things. So they went, I think, asked us for the cosine of 0.01. So according to our thing, we could use our best polynomial, the sixth order, and plug in 1 minus 1 half 0.01 squared plus 1 over 24.01 to the fourth power. And it seems like this is a lot of work, right? Remember, the calculator can't hold a whole infinite number of stuff in its head. The calculator can't do cosine of x. The calculator says cosine of x, that's an infinitely defined continuous function. I don't know how to understand that. The calculator does understand discrete points that can come from Maclaurin or Taylor polynomials. So if you're wondering why you're doing this, there's a lot of reasons. That, I think, is one of the primary reasons you should be aware of at this point. Anyway, let's see what they note down here. Note that in this example, we only have even powers of x. It says Maclaurin polynomials for sine of x have only odd powers of x. That's one of your exercises. I'll probably give you that one. But that's not always true. It depends on what the functions are, and also if they're Maclaurin, or what C is. Okay. Let's look at sine of x example, and instead of doing Maclaurin, let's go a specific interval. So once again, take some derivatives. Start out. Sine, cosine, negative cosine, and then it would repeat, right? The derivative, let's do it in there. The fourth derivative, better make sure we use the right notation, of x would be, what's the derivative of cosine? Negative sine, so negative sine, hey. We would be back to the beginning, wouldn't we? And then we'd just cycle down again. Anyway, then plug in C, so it looks like we got some unit circle things here. Sine of 30 degrees is a half. Guess we could check that over here. 1 square root of 3, 2. Sine is a half. Cosine is root 3 over 2. Okay. And then there we go. So we've got some coefficients. So let's put those in green again. I just like being consistent. And then the Taylor polynomial is going to be that first coefficient plus the second coefficient times, we want it to be centered, so here's your x minus c. And then the third coefficient is 1/2, so there's your 1/2 minus 1/2, right? And you've got a 2 factorial on that one, x minus c squared. And then the third coefficient is negative root 3 over 2, and 3 factorial, and an x minus c cubed. And you can see that even when you look at just the third Taylor polynomial, look how close it hugs sine of x until you get fairly far away from where we were looking at pi over 6. How the center was right here, right? Not at 0. But notice it's a very, very close approximation. And a computer can handle something this small incredibly easily. It has lots of storage. It just can't do infinite stuff. You can't say, hey, computer, you know that function like we do in Algebra 2 even, maybe even in Algebra 1. You can't be like, computer, you know that the function natural log of x has this kind of a shape. Just memorize that shape, computer, and make sure it's perfect everywhere. The computer doesn't know what you're talking about when you say things like that. Anyway. All right, one more. This time, let's do natural log of x. So we want to approximate a value, just like a computer would do. The computer says, how do I get the natural log? Oh my gosh, I always do natural log funny. How do I do the natural log of 1.1? So like when you enter that in the computer, what's it do? It does something akin, maybe even exactly, I'm not sure what our 83 does perfectly, but it does something akin to right here. It creates a high-order Maclaurin polynomial, and it centers it, since this is 1.1, this says the computer understands that, hey, I should center it at 1. So once again, we'll create a Maclaurin polynomial. So here's some derivatives. I think that those are all pretty easy for us to follow at this point. Notice how they left the parentheses here, though. So then we plug in, we wanted to center it at 1, right? So notice how we're plugging into the function natural log of 1 plus x. So that's a little different on this example. Anyway, so we're plugging in. So it looks like the center of, I think I said something quite slightly off. The center is 0, so this is Maclaurin. As soon as I saw the word Maclaurin, I should have known the center was 0, right? But anyway, it's just the function's been selected a little bit differently this time. So this function has that 1 embedded in it that I was talking about. Anyway, so we plug that in, obtain our coefficients. I'll be consistent and put them in green. And then we create, looks like they went with a fourth order. That's good enough for us, I guess. So fourth order polynomial is going to be, we pull 0 for the first one, so nothing there. This is Maclaurin, right? So it'd be x minus 0. So then we have 1x minus 0. Then we have a negative 1 over 2 factorial, x squared. And then we have a positive 2. Where's the 2? Hey, remember this is like this guy right here. It's like 2 over 3 factorial. That's why it's 1/3, 2/6. Anyway, and well, hey, where'd the negative 6 go? Remember this guy. Did that again. Negative 6 over 4 factorial. That is negative 1/4. Anyway, so you plug that in and you get this number. Let me compare with the graphing calculator, because I bet it uses more than a fourth order polynomial. So if you plug that into your graphing calculator, the natural log of 1.01 is, from my calculator, I'll just give you a hint. 1.01 from my calculator, and I don't know what order it's using, but it's almost identical. And I bet that is just because this approximation is so good. So when I plugged it into the calculator, here's what I got. So how many decimal places do these equate to? So 953 looks like they're equivalent all the way out to the 10,000th place, and then it's slightly different after that. So a pretty darn good approximation. I hope you found this valuable. It depends what I've given you for the assignment this year, so I won't include the video. See you next time.